Terbium belongs to the lanthanide family, often called rare earth elements. These are metals with very similar properties, which makes them difficult to tell apart and even harder to separate. Terbium itself is silvery white, ductile, and malleable. But unlike familiar metals like copper or aluminum, you won't find it naturally in metallic form. It's always locked up in ores with other rare earths. At first glance, terbium might not look like anything special, just another shiny metal. But what makes it remarkable is how a relatively small amount can have such a huge impact on modern technology. From wind turbines to defense systems, terbium plays a hidden but essential role in the way our world operates today. In 1843, Carl Gustav Mosander discovered terbium while working with yttrium samples. The tools of the 19th century weren't precise, so for decades, terbium and other rare earths were often mixed up or misclassified. For a long time, terbium remained more of a scientific curiosity than a practical resource. Its breakthrough came in the 20th century, when it was used in green phosphors for color televisions. That application turned terbium from a lab oddity into a valuable industrial material, setting the stage for its use in modern electronics and renewable technologies. Here we get into one of the most challenging parts of terbium's story: how we actually separate it from its ores. Pictured here is bastnasite, one of the main minerals where terbium is found. But here's the catch. Bastnasite doesn't just contain terbium. It contains a whole cocktail of rare earth elements, all with nearly identical chemical behavior. Separating one from the other is like trying to sort grains of sand that all look and act the same. The process begins with mining, often in large open-pit operations. Once extracted, the ore is crushed and ground into fine powder. This makes it easier for chemicals to react with the minerals. Next, we use acid leaching or alkali treatment to dissolve the rare earths into solution. At this point, terbium is mixed in a liquid soup with dozens of other elements. The heart of the challenge is the solvent extraction process. Imagine a series of hundreds of chemical washing steps, each designed to pull terbium a little further apart from its neighbors like dysprosium and europium. These steps are repeated again and again, sometimes thousands of times to achieve the necessary purity. Once terbium is concentrated into an oxide, we need to reduce it to metallic form. That's usually done through electrolysis, where electricity is used to strip away oxygen atoms, or through metallothermic reduction, where reactive metals like calcium pull the oxygen out of the oxide. This entire process is extremely energy intensive and produces significant waste, including radioactive byproducts. That's why rare earth refining has raised serious environmental concerns. Today, the world's supply of terbium is dominated by China, particularly from the Bayan Obo mine in Inner Mongolia. China controls 80 to 90% of global production, giving it enormous leverage over supply chains. What makes terbium production tricky is that it's not mined for its own sake. It's typically produced as a byproduct of other rare earths like neodymium, which is in high demand for magnets. This means terbium's availability rises and falls depending on the demand for those other materials, making its supply inherently unstable. Countries like the United States have restarted rare earth mining at Mountain Pass, but refining capacity still largely resides in China. This reliance has led governments to classify terbium as a critical mineral, one that is essential to national security but vulnerable to supply disruptions. Here you see a sample of terbium itself. It may look like just another piece of shiny metal, but its properties are what make it unique. First, terbium is soft enough that you can cut it with a knife. It also oxidizes slowly, so while it doesn't rust immediately, it will tarnish over time. It has a melting point of around 1,356 degrees Celsius and a boiling point over 3,100 degrees Celsius, making it stable at high temperatures. But what really sets terbium apart is its magnetostrictive property. When alloyed with iron and dysprosium, it forms terphenol D. This alloy can change shape when exposed to a magnetic field, expanding and contracting slightly. This might sound subtle, but it's revolutionary for engineering. The molten metal background reminds us of traditional metallurgy, but terbium is different. Unlike iron or aluminum, we don't shape terbium into beams, wires, or sheets. Instead, it's processed in small amounts for highly specialized purposes. One of the most important products is terphenol D, the alloy made with terbium, dysprosium, and iron. Thanks to its magnetostrictive properties, terphenol D is used in sonar systems for submarines, precision actuators in robotics, and even in smart materials that can respond dynamically to magnetic fields. This ability to literally move under magnetism makes it a cornerstone of modern sensing technologies. Another key use is in phosphors. Terbium compounds glow a brilliant green when exposed to ultraviolet light. This glow is used in LED displays, fluorescent lamps, and even in the security features of banknotes. In other words, terbium isn't just supporting heavy industry, it's also shaping how we see and interact with the world. Processing terbium requires a level of care and precision that reflects its rarity and cost. Even tiny amounts can have a big impact, so engineers focus on maximizing efficiency and tailoring its use to applications where its unique properties make the biggest difference. Terbium's applications are wide-ranging. In renewable energy, it strengthens magnets for wind turbines, ensuring they perform reliably under high heat and stress. In defense, its alloys support sonar and advanced sensing technologies. In electronics, terbium gives us vibrant LED displays and efficient lasers. And in medicine, it improves imaging quality for X-rays. The biggest challenges for terbium are sustainability and supply security. Mining and refining are environmentally damaging, and the world remains heavily dependent on China for supply. Recycling could help, but the technology is still developing, and recovering rare earths from e-waste is expensive and complex. At the same time, no substitute has been found that matches terbium's magnetostrictive and optical properties. That means the world will continue to rely on it, making the push for sustainable production and diversified supply chains all the more urgent. Terbium may not be a household name, but it plays a vital role in modern life. From powering renewable energy to enabling advanced defense systems and enhancing the screens we use every day, terbium is a hidden engine of progress. The challenge for engineers, scientists, and policymakers isn't whether we use terbium, it's how to secure its future responsibly. Its story is one of hidden power, and its future depends on innovation, sustainability, and global cooperation.